Welcome to this short introductory presentation about sputter profiling in low-energy ion scattering, also called LEIS. LEIS is usually applied for the analysis of the outer atomic layer with ultimate surface sensitivity. The elemental composition of this layer is determined quantitatively. Also, information on the composition of the first few nanometers of the sample are gained from the so-called in-depth information, which is contained in the spectrum and does not require any sputtering. There are, however, cases where additional depth profiling is required. Sometimes the depth range of this information is not sufficient, or an element is not present at the surface and therefore cannot be identified from just the in-depth information. It is important to note that light elements do not show the in-depth information at all. In these cases, classical sputter profiling can be applied. Just as in other surface analytical techniques, LEIS analysis can be done while a second low-energy ion beam creates a sputter crater. While sputtering, surface spectra are acquired from the receding surface in the crater, forming a depth profile. Using separate beams for analysis and sputtering allows the operator to optimize the ion beam parameters for each task. Usually 500 to 1000 EV argon ions are used to form the sputter crater, while the analysis beam is chosen according to the analytical requirements, especially the mass of the elements of interest. A sputter depth profile through rather thick nickel-chromium layers shows a nice dynamic range of about 3 orders of magnitude plotted on a logarithmic concentration scale. More importantly, the quantification is very easy and linear. In this two-component system, a correlation plot of the two intensities versus each other shows a perfectly linear behavior, as is typically the case for LEIS. This is proof that even in the interface region where the two metals mix, no matrix effect occurs. Taking the sensitivity factors from the layers of pure chromium and nickel, the intensity scale is converted into a concentration scale. Plotting the same profiles on a linear scale and showing the sum of the two signals, the blue dots, illustrates how well the two signals add up to 100% over the whole depth range. This slide shows a more practical application from the field of semiconductors. Manganese-based diffusion barriers for ruthenium films were studied with 1, 2, and 5 nanometers of ruthenium covering 1.5 nanometers of manganese. The 3 kV LEIS spectra are shown after atomic hydrogen treatment. Only oxygen and manganese surface peaks are visible. The ruthenium surface peak is not visible due to shielding by adsorbed hydrogen, a special property of ruthenium under these conditions. The high amount of manganese visible at the surface, even for the thickest ruthenium overlayer, is noteworthy. How is this manganese distributed over depth? Sputter depth profiles using 500 EV argon to erode the surface were required. Manganese, shown in orange, is strongly enriched at the surface, but as expected also present at the interface below the ruthenium layer. Within the ruthenium layer, the manganese concentration is at its lowest. By heating the sample to 300 degrees C, the enrichment at the surface is strongly increased, indicating that the manganese at the surface is due to diffusion through the ruthenium film. To summarize, sputter profiling in LEIS is an additional option to the in-depth information already contained within the spectra. It extends the depth range from a few nanometers to some tens of nanometers. It helps in the analysis of complex samples and multilayers and can allow one to measure the depth profiles of light elements, which are not accessible to the static in-depth information. For more information, please visit www.iontof.com/qtech.